Excellent. Hi, my name is Dan Callahan. You can find me on Twitter at Callahan, and then you can go from there to my Mastodon because Lord only knows what's happening to Twitter these days. I'm going to talk about why WebAssembly matters on the back end, and I'm going to do that by starting to talk about the origins of WebAssembly. So WebAssembly came out of the browser, as you might imagine, because it starts with the name web. And if you think about the browser, you think about the web technology stack. It's more or less been HTML, CSS, and JavaScript since the mid 90s. So a quarter century ago, you had the foundations for the modern web. And if you wrote a website, if you wrote content using these back then, it'll still render today on devices that didn't exist back then. You can take it. The web works on your phone. The web works on your car, at least my car, and I don't know why, but it's there. When your laptop vendor decides to go and convert from Intel to ARM architecture for its CPUs, no problem. The web goes with it. And the web goes with it because the web is built on these open standards that are very carefully considered to be durable and portable and transferable. But there is a problem with the web stack, and that's JavaScript. And JavaScript isn't a problem because of anything inherently wrong with JavaScript. JavaScript's a problem because JavaScript is the only choice on the web, and there is no one language that is the best tool for every job. Moreover, JavaScript's a high-level language. And when I say high level, I like to think of programming languages kind of on a continuum where lower level languages give me more control over memory, higher level languages don't, but in exchange, I don't have to think about that. So at the low level, you've got Rust and C. At the high level, you've got Python and JavaScript, and somewhere in the middle are things like Swift and Go. And and the thing about these high level languages is they give me more productivity because I don't have to worry about those things, and more safety because they do it for me. But they also have these strong opinions. So JavaScript has opinions about what a string is, what an object is. Until recently, JavaScript didn't support integers. It only supported floating point numbers. And again, that means that there are some places and some problem domains that JavaScript just can't address. But that's all we have on the web. On the back end, we have this entire breadth of every programming language available to us. We can choose Python where it makes sense. We can choose Rust or C where it makes sense, or Go or Swift or C#, whatever we need. We can pick the right tool for the job. And what we need to do is find a way to bring that same sort of flexibility to the web. We need a lower level complement to JavaScript. But we can't just pick another language. We can't just say, okay, the web is HTML, CSS, JavaScript, and Rust, because no two languages are the best tools for every job. It's this kind of, sure, I'm sure there's some, asymptotic approach that you can get to. But what you really want is the same flexibility you have on the back end. But for something to be suitable on the web, it has to have three properties. It has to be universal. Again, the web goes everywhere. It's on your smartwatch. It's on, it's in your car, most likely. It's in SpaceX's capsules going up into low Earth orbit. Web interfaces and the web technology stack is ubiquitous. It also has to be safe, which means that anything we build on the web it goes through this amazing crucible where the core of the experience of the web is running untrusted code safely. Every time you go to a website, that website sends a bundle of JavaScript to you, and you run that code, that completely untrusted code, on your computer, and you trust the design of the web ecosystem, the web platform, to keep you safe. So any technology coming out of that is also going to have that property, and probably more so than things that are developed in less hostile environments. Lastly, it has to be fast because we're doing this every time you open a new tab. And in resource-constrained devices like smartphones, smartwatches, older laptops, whatever. So we go back to this list of the various languages on this continuum. The reason you can choose from any language on the back end is because you have access to machine code. You can compile C to run on an Intel processor on Windows, or you can compile it to run on an ARM processor on macOS. And that's great, and that's fine. But we can't do that on the web because the web can't be tied to any specific machine, because we don't know where the web is going to go. It's lasted a quarter century. It needs to last another quarter century. And so we can't bake in assumptions about where it's going to run. And so when we go to try to figure out what the equivalent to machine code would be for the web, that's where you start getting the design origin of WebAssembly. It's this idea of kind of an abstract machine code that takes the least common denominator between ARM and Intel and MIPS and says, all right, what do you need to be a really basic credible processor, a credible CPU instruction set? And so all WebAssembly really knows about at its core, it's an instruction set. It knows about numbers. It has floating point numbers and it has integers. It knows about functions and it knows about memory. And that's pretty much it. The idea is that just like you can compile any of those other languages to target any other CPU or operating system, you can also compile them to target WebAssembly. And then you take that WebAssembly module and give it to a runtime like your browser. And that just in time does that final trip into machine code and does that final step of translation. More concretely, it might look something like this. I have a function in C that takes an integer, returns an integer, and just divides it by 4. In WebAssembly, when I compile that, I get a binary out, but if I then decompile the binary, the textual representation might look something like this, where I have a function foo. It takes a parameter that's a 32-bit int. It returns a result that's a 32-bit int. And the body of the function gets that passed in parameter, gets the constant value of 4, does a signed division operator against both of them, and returns the result. I can take this module, give it to my browser, and then it's the browser's job to convert that into WebAssembly, or from that WebAssembly module into assembly code specific to the operating system and processor and whatever else it's running on right now. More abstractly, I can have a single wasm module whose original source code was in whatever language I like working in, Python or Rust or JavaScript or whatever. I can then give that to a browser on a laptop or a phone or a node environment on a Raspberry Pi, and that will then take care of converting it down to the machine code that it needs to be to actually be executed on that platform. In the same way that we give JavaScript to those devices and expect those to have a runtime that can just in time compile it and execute it efficiently there. But the key thing is, I don't have to worry about any of that. I just have to worry about compiling to this one target, a wasm module. And this has been possible for half a decade. So since October 2017, every major web browser has shipped WebAssembly on by default. If you've ever used Figma, you've run WebAssembly in your browser. If you've ever watched an Amazon Prime Video or Disney Plus or the BBC iPlayer, you've used software that has components built in WebAssembly. And so since 2017, the web technology stack is not HTML, CSS, and JavaScript, it's HTML, CSS, JavaScript, and WebAssembly. But for you as a developer, it's not even this. It's rather HTML, CSS, JavaScript, and fill in the blank. And you can put whatever language you want into that blank, so long as it can compile to WebAssembly. And at this point, virtually every language has some support for going to WebAssembly. Python 3.11, which just released, is starting to have native support there as well. Like we're getting to the point where if you can write it, you can find a way to run it in WASM. That's the front end. Let's talk about the back end. When you take all this together, what you have is you have to build something that's universal, safe, and fast. And it turns out that's really useful, not just in the browser, but also in the back end. When I talk about universal, what I mean is if you look at something like Node Sass, which used to be the standard way to interact with the Sass CSS library, what that was a Node module that was a really thin wrapper around a C++ library. And it was written in C++ libsass because that's a portable language. As long as you know what you're targeting, you can compile that however you need it. So for 32 or 64-bit Intel, for ARM, whatever. The JavaScript wrapper, the bindings stay the same, your interface to Node Sass stays the same, but that library in the middle changes shape depending on what CPU you're intending to run it on. And so you can compile it to any CPU. You also have to have different flavors for every version of the operating systems and every version of Node. And so you end up with this kind of combinatoric explosion. You can use this library anywhere, but it's bound very specifically to where it's running. And that causes a problem because back when Node Sass was more active, they had this matrix of supported environments of operating systems and CPU architectures and Node versions. And on every release, they would go and build literally hundreds of megabytes of binaries pre-built saying like, all right, here's Node Sass for Windows. Here's Node Sass for 64-bit Windows. Here's Node SAS for Linux. Here's Node SAS for Mac OS. And then each of those times, whichever version of Node you were targeting. The problem here, in addition to just being a combinatoric explosion, is that it doesn't do anything to address the web. And this kind of typifies the schism in between backend and front-end JavaScript development. On the backend, we did have access to machine code, but machine code's bound to a machine. And so we couldn't bring that sort of development, that sort of experience back up to the web. That's what WebAssembly tries to address, or one of the things it tries to address. Getting rid of this massive matrix of combinations, instead giving you a single compile binary artifact, for example, libsas.wasm, that you could wrap in JavaScript, and you're done. That one artifact can be sent everywhere, and then the runtime, your browser handles, making that WASM module executable for your architecture. As fate would have it, Node SAS didn't actually take this trip. They actually rewrote the whole thing from C++ to Dart, which compiles to JavaScript. But then there's also a project that Google's working on to compile Dart to WebAssembly. So that's all going to work. As of last week, most of the test suite passes. But the point is, you end up with one artifact by targeting WebAssembly. It's self-contained, and it doesn't care where it's running. It doesn't care about the operating system. It doesn't care about the CPU. You can be running on an Intel thing. You can go throw it on your M1 Mac. The same thing will work both places. Awesome, just like the web. It also has to be safe. The way WebAssembly is safe is the same way that JavaScript is safe. When you think about JavaScript, on its own, JavaScript can't do anything to affect the outside world. Sure, it knows about strings and objects and things like that. But if you want to do something like log a message, you have to depend on the console.log function that's provided from the environment that your JavaScript's running in. So the browser provides console log. The browser provides Canvas APIs for drawing on the screen. The browser provides other functions. And because it's up to the runtime to determine what sort of functionality is available and how it's available, that runtime can mediate what your JavaScript is allowed to do. So the web defines APIs for accessing cameras and microphones, but if I try to do that, the browser stops and says, wait, hey user, do you want to allow this? And only if the user consents does the JavaScript get access to the outside world in that way. The careful design of these APIs, the careful design of the system of both the language and the APIs around it, is what makes the web safe. So you've got the web stack. The obvious question gets asked by Ryan Dahl, which is JavaScript is great on the web. Is it also great on the server? And so he rips the JavaScript engine out of the server and makes Node.js. But without the rest of the browser providing things like the DOM APIs, Node has to come up with its own. And Node takes the same path that most server-side programming languages did at the time, which is it gave the running JavaScript access to more or less everything the user running it has access to. So if you're logged into your developer account and you run a Node module, there's a chance that Node module is going to go and do something like try to rate a cryptocurrency wallet. And this has been a problem. It's not specific to Node. You see similar things in the Ruby Gems ecosystem and in the Python PyPI ecosystem. But I mean, back in 2019, headline, yet another malicious package found in NPM, this time targeting crypto wallets. It's hard to design APIs that are safe. But it's that combination of the language and the APIs that produces a safe system. And so you see things like Dino, which is an alternative server-side JavaScript runtime that's trying to hew a lot closer to the way browser APIs work instead of Node's own like file system module and things like that. And in doing that and being denied by default, Dino tends to be a little safer. Long story short, because everywhere the web goes, so goes WebAssembly. Well, now everywhere that can run the world's most popular programming language can also run any programming language that compiles to WASM. And they can use whatever APIs are available. So if you're using WASM inside a Node environment, you can expose Node APIs to it. You have to kind of write that glue code yourself right now. But the idea is that whatever capabilities the enclosing runtime has, what your module can do is limited to that. I'm going to go over by about 3 or 4 minutes. I apologize. The obvious question then is, all right, what if we get rid of the JavaScript runtime? What APIs are we going to use then? And there are standalone WebAssembly runtimes, and you might do this because you want something that's smaller, more self-contained, whatever. There are WebAssembly runtimes that fit inside databases, that fit inside the secure element of your CPU. Fastly's entire compute at edge project is built around WebAssembly. And the APIs that this community is starting to settle on are called WASI, the WebAssembly System Interface. And these are all built around deny by default capabilities. It's still a work in progress, but it's being developed as part of the wasm time WebAssembly runtime in the Bytecode Alliance, which is kind of a multi-vendor consortium trying to standardize what WebAssembly should look like outside of the browser. And this stuff's real and it's production ready. If you just have a WASM module and you want to run it on your server, WASM time will do it for you. And it's been in production since September. It's been in production over a year at Shopify. It's been in production more than half a year at Fastly, over a year at Microsoft. This stuff's real and it's mature and it's fast, because the other thing the browser has to do, like I said, is it has to be fast with whatever we add to that stack. There's a startup in this space called Cosmonic, and they've been showing this graph where they're saying, hey, we're slowly virtualizing more and more of the underlying stack that our code's running on. And I think this message is important because it kind of boils down to, look, traditionally we had virtual machines. Now we have Docker containers. Now we have WASM modules. And you don't necessarily, like, none of these are necessarily superior to the others. They give you a set of tools and a set of choices. Are you going to virtualize the whole computer or the whole operating system or just some functions? And depending on what you want to do, you might choose a different one of these. It gets a little confusing because Docker just announced that they're going to support running WebAssembly modules directly inside Docker. But the whole idea is that with virtual machines, you get to control the whole shebang. You can virtualize the kernel, you can virtualize hardware, whatever. WebAssembly modules, they just have functions. They don't know about the outside world. And so depending on what you need, you can choose the right thing. WebAssembly modules are smaller and start faster. Virtual machines are larger, but give you more control and more options. But what do I mean when I say smaller and starts faster? As part of the WasmTime 1.0 announcement in September, the team took SpiderMonkey, which is the JavaScript engine built into Firefox. It's millions of lines of C++. They compiled it to WebAssembly. And they got its instantiation, or initial instantiation time, down to 5 microseconds. 400 times faster than what it was. It was 2 milliseconds in the previous version of wasmTime. But you can take these modules, and because they are so tightly scoped and they're so small, I mean, you're usually talking single-digit megabytes for that versus hundreds of megabytes or gigabytes for a virtual machine. These things are really fast, and they start quick, and they don't take up a lot of space, and you can move them over the network really fast. And that means you can put them in places that you wouldn't normally put other things. Hence Fastly's compute at edge being built on WebAssembly. They can chuck a whole load of WebAssembly modules all over the world, start them up on every request, throw them away when it's done, and there's not much cost, there's not much expense, it just goes. So that's WebAssembly on the server side. These properties that made it useful in the browser are also really useful on the server side. You get a safe sandbox runtime, you get a universal binary format, and that means that you can run any language, anywhere, safely. One example I'm gonna pitch, plugins. I work at a startup called Suborbital. Our whole deal is that we're trying to make it possible to extend SaaS applications with user-defined plugins. WebAssembly is the first thing that makes this possible to do kind of efficiently at small scale. You could throw virtual machines at the problem all day long and have something like GitHub Actions, but we want something really small that can run in situ. One of our customers, Avenue, does database monitoring and alerting. And so they'll run a SQL query for you, and when certain results are returned, they can trigger an alert. But it's hard to express everything you might want to do in SQL. So they went and built in a thing where you can chuck whatever JavaScript you want at them. We take that, we compile it to a WebAssembly module, distribute that inside their Kubernetes cluster, and every time you get a result, they can process that for the user using user-provided code. They don't have to build their own integrations. WASM keeps it all safe and efficient. And these things are, again, just like single-digit megabytes. You can move them everywhere. They're quick to move. That sort of use case is what WebAssembly is empowering and enabling on the server side. That's one of the things I'm excited about. Trailheads for the talk. Bytecode Alliance is where a lot of the server-side WASM development's happening. That's where you'll find things about WASI and wasmTime. Cloud Native WASM Day as part of KubeCon just happened a month and a half ago. All the recordings are on YouTube. If you want to find out more about running WebAssembly on the server, that's the place to be. Really good videos, really good keynotes. There is talks from the Docker folks about why they think they need to have WebAssembly support natively inside Docker as a complement to full container images. Highly recommend checking it out. The end. Questions?
Awesome. Thank you very much, Stan. That was very, very cool talk. I'm very lucky that I caught like the full one in NIDevConf. Whenever the talks are released, like it's definitely one to go check out. Like actually, even before I get into questions, like one thing you touched on, like the Node SAS, like I've had to try and explain to so many people like why I have to do like npm rebuild Node SAS every time I change my Node version.
Yeah.
It's just what? Why?
There's a version that's built on Dart now that just compiles to straight up vanilla JavaScript, which is a lot more convenient for that use case. And that at least gets you libsass inside Node, inside the browser, inside Flutter. It doesn't give you it inside a pure wasm environment, but again, you could take libsass and do that if you needed to.
Yeah, and like I get like even with the whole WASM stuff, like it's in the browser, and when I'm running Node SAS, it's on my machine. It should be compiled to the binary of my machine and should work. But yeah, I'm going off topic. Yeah, so with a question here from Dermot, can you compile JS/TS to WASM? Would you get any of those optimizations / benefits? Do we need to go learn Rust? I'm not learning Rust anytime soon.
So yes, you can. Some of the initial messaging around WebAssembly was, especially to JavaScript audiences, was like, you can keep using JavaScript. It's fine. This is a complement. It's not a replacement. Because it's kind of scary to have someone show up, especially if you're on the front end world, and say, hey, suddenly all these people that use Rust and C++ are going to be playing the same sandbox. Like, what's going on? I think it's important to note WebAssembly will not necessarily run faster than JavaScript. JavaScript engines are extraordinarily well optimized. If you have algorithms that really benefit from manual memory management, sure, you can get that. But if you're on the back end, you can also run that code natively. What you're really looking at WebAssembly for is the sandboxing and the kind of universal binary aspect of it. So if you're compiling JavaScript to WebAssembly, which at Suborbital we do quite a lot, that's the primary language people use when they embed our product. What we're doing is we're actually packaging up a WebAssembly or a JavaScript runtime, compiling that to WebAssembly, then putting the JavaScript in it. There are several of them. Shopify has a project called Javi that we rely on, that is meant to take untrusted JavaScript and compile it into a completely self-contained binary that's WASM that you can then run anywhere. You're not getting more optimization. It would run faster as raw JavaScript, but it runs fast enough. And what you're getting instead is just really, really good controls around safety. This is the same sort of thing that Figma was doing to run user-provided plugins written in WebAssembly. They want the safety, not necessarily the performance characteristics.
Yeah, I find that interesting. Like when I was a young developer, it was sold to me that like Java was the like write it anywhere, build it, run it anywhere kind of language. And now it seems to be it's shifting towards not necessarily JavaScript, but like WASM is like the solution for it now. Like what was the kind of shift there? Like why did Java fall to the wayside?
So I think there are two things. One, you should definitely be careful in that WebAssembly has, I mean, it is ubiquitous. I guarantee you have interacted with software and probably have software on a device somewhere in your home, i.e. Amazon Prime Video or Disney Plus, that is built on WebAssembly. So it's real, but there is a lot of hype that I'm not sure is entirely justified. So like, don't go throwing all your tools out right now. The comparison to Java is apt because it's kind of the same story. Write it once and it'll run anywhere. WebAssembly will run anywhere that the web goes, and the web is going flipping everywhere. The thing that's different is we've learned a lot. It's been decades since Java was first introduced. We've learned a lot since then about making something that is small, that's efficient. The JVM is an amazing piece of technology, but it tends to operate at a higher level. The JVM has a garbage collector built in. It has notions around what an object is and dynamic calling and things like that. WebAssembly doesn't. WebAssembly is much closer to the simplest possible CPU you could build, not an entire full-fledged VM. And so the benefit is that it starts up much more quickly, and we've designed it in a way that the APIs that are available are a lot easier to sandbox and use safely. So you're gaining ubiquity and you're gaining efficiency over the JVM. That said, the JVM, again, once it starts up and warms up and can jet all your code, it can fly, but it's a big beast. WASM modules are teensy tiny.
Yeah, I don't want to write Java anymore. I want to write JavaScript. I want to be in my comfort zone. Even like kind of like lean on that kind of question. I think it was one of your slides you mentioned about like the Bytecode Alliance that took the Spider Monkey engine. Whether you know or not, like, was there a clear decision to choose the Spider Monkey engine over, say like the likes of V8, and potentially is like Bun coming in deployment of that? Like, how is that going to affect like decisions going forward?
So the Spider Monkey engine was just a kind of, we needed a large module to test WASM time performance on as we were approaching 1.0. And that just happens to be a really nice self-contained code base that was amenable to being compiled into a big multi-megabyte WASM module. There's nothing special about Spider Monkey or WASM time or WASM connected to that. I imagine the same thing could have been done with V8, but just the people working on it had a lot of familiarity there. If you go back way in the history of WebAssembly, there was kind of a competing technology coming out of Google at the time called native client, where they were trying to compile code to closer to LLVM's intermediate representation, but that's not quite as universal of a representation as other browser vendors thought was necessary for something to be part of the web. And so Mozilla and Microsoft kind of came to the table with an alternative proposal that turned into WebAssembly and eventually got Google on board. The engineers that were working on WASM Time 1.0 are ex-Mozilla, so they probably just have more familiarity with SpiderMonkey. That's the real inside scoop on like, well, why was that the benchmark? That's what the people that were doing the benchmarking knew.
No, yeah, cool. That's cool to know. And then I've got like one more question here. If anyone on the Zoom has any questions, like feel free to be on mute or whatever. I think the question kind of asking is, it's interesting myself as well. Like, obviously, you'll bundle up part of your application into WASM, and then maybe the rest of it will be raw JavaScript. What is like the cost of talking back and forth? Like, I'm thinking of like the days of like, web workers, service workers. Is it the same kind of feel and experience?
There are some cases. So in the early days, it was a pretty heavyweight thing where you had to be serializing things and sending them across this boundary and bringing them back and doing these messages. There are cases where it is actually more efficient now to call in between JavaScript and WebAssembly than between JavaScript and JavaScript. The key thing to look for as far as where the future is going, there's something called the WebAssembly component model. And what the folks at the Bytecode Alliance and the folks working on WASM Time are trying to do is define this common grammar where you can say, all right, here's what a string looks like. And then each runtime can make their own conversion from like, all right, here's how I take a Python string and turn it into a WebAssembly string. And then the Rust side can say, here's how I take a WebAssembly string and turn it back into a Rust string. And if you have that interface well specified, you can actually pass data in between languages with little to no overhead. That's all in development. We should have a working version of the component model by the end of the year, next year. But basically, you shouldn't be worrying about calling overhead. There is overhead, but it's not. It soon will not be significant, and in many cases is not super significant right now. And the power, once we have those interfaces again, is that this isn't just about JavaScript calling into libraries written in other languages. You can start calling in between arbitrary languages as long as they can both compile to a WebAssembly module. And because WebAssembly is so small and the runtimes are so small and efficient, you can start embedding a WebAssembly runtime in your own programs written in whatever language you want to provide, again, user extensibility or whatnot. There's an alternative to Tmux called Zellage, that all of its user plugins are written in WebAssembly. And I think we're going to see more and more of that, in the same way that if you're a Vim user or a Neo Vim user, or if you've looked at like World of Warcraft or other video games, it's common to embed a scripting language like Lua because it's small and expressive, and you want the users to be able to do their own code. Well, with WebAssembly, you can embed a WASM runtime much the same way, but you don't have to dictate what language your users are using. Any WASM module can call in between any other WASM module. There's an open source project called Extism, EXTISM, that is really trying to drill down on how do you make that sort of interop really nice and clean. But yeah, it's really neat, the multilingual stuff that's, I think, right around the corner for us.
I guess, and then the last thing, like as a predominantly Chrome user, I rely on my Intel MacBook to like heat my house whenever I open up Chrome and a couple of tabs. Does WASM like affect in the same way that like running a bunch of JavaScript on a Chrome tab, or is it like just knowledgeable?
I mean, it shouldn't. WebAssembly should be, in the context of the web, it shouldn't be meaningfully different, but frequently is frequently more efficient. So you'll see lots of reports from like WordPress when they were working on the Gutenberg, their new editor for WordPress. They had an example implementation of WebAssembly which ran at like 100x the speed of the built-in one, and that was because they could use a language that had more control and could give more hints to the compiler. Because JavaScript, like, sure, you've got types, but like JavaScript ain't TypeScript. Your browser don't know TypeScript. So there are optimizations you can do ahead of time in WebAssembly you can't do in JavaScript, and that sometimes gives you much more efficient code. I'll second the comments in the chat though. As an ex-Mozilla employee myself, give Firefox another shot. It's pretty good. It's pretty darn good.
I know I need to like if you're like podcast listeners and you listen to like the syntax podcast, like Wes Boss and Scott Tennessee are like they're loving Firefox at the minute. It's amazing, and I don't know. I love the pain of Chrome. It's terrible and it never works half the time, but I love it.
No, I mean there's excellent engineering everywhere. On a personal level, I think it's important that someone is in the browser game, given how important the web is. That's not motivated by profit and surveillance, and Mozilla is truly a nonprofit. So, browse for good. Use Firefox.